Good day everyone. So our group of thermodynamics chemical engineering will be explaining about synthetic fuel industry. So this is our teammates. Our leader is Ami Ashraf and myself Imran Azmi, and then Tan Kar Hui and lastly Chiu Tong Ling.
Good day everyone. Today we will be presenting about the synthetic fuel industry and its thermodynamic analysis. Synthetic fuel, also known as syn fuel, is an alternative fuel produced from non-petroleum resources. In this presentation, we will discuss the types of synthetic fuel, production processes, important application opportunities, and future outlook of the industry. Synthetic fuel is fuel produced from non-petroleum resources through chemical conversion process. The raw materials commonly used include coal, natural gas, biomass, and municipal waste. Synthetic fuels serve as an alternative to conventional fossil fuel, such as crude oil. It is developed to improve energy security and reduce environmental impact compared to traditional fuel. There are several types of synthetic fuel. First is synthetic diesel, which is commonly used in diesel engines for trucks, buses, and heavy machinery. Second is synthetic gasoline, which can be used in normal gasoline vehicle without major engine modification. Third is jet fuel, which can be produced from biomass, natural gas, or coal, and is widely used in aviation. Lastly, methanol is used as fuel additive, and chemical feedstock in many industries. The first production process is gasification. Gasification converts carbon-based material such as coal, biomass, and waste into synthesis gas, also known as syngas. The process occurs at high temperature with limited oxygen or steam. The main product forms are carbon monoxide and hydrogen. Syngas is an important raw material used for synthetic fuel production. The second process is Fischer-Tropsch synthesis. In this process, syngas is converted into liquid hydrocarbon, such as synthetic diesel and jet fuel. Catalysts such as iron or cobalt are used under high temperature and pressure conditions. Carbon monoxide and hydrogen react together to form long-chain hydrocarbon. This process produces cleaner fuel with low sulfur content. The next process is pyrolysis. Pyrolysis is the thermal decomposition of biomass or waste materials in the absence of oxygen. This process produces bio-oil, syngas, and solid shock. The bio-oil produced can be upgraded into synthetic fuel product. Pyrolysis is important because it helps convert waste material into useful energy sources. Another important process is reforming. Reforming converts hydrocarbons such as natural gas into hydrogen-rich syngas. Common methods include steam reforming and partial oxidation. For example, steam reforming reacts methane with steam at high temperature to produce hydrogen and carbon monoxide. The syngas generated is later used in methanol production and Fischer-Tropsch synthesis. Synthetic fuel is important for several reasons. First, it improves energy security by reducing dependence on imported crude oil and diversifying fuel sources for countries with limited petroleum reserves. Second, it provides environmental benefits because it produces cleaner combustion with lower sulfur and particulate emission. Greenhouse gas emission can also be reduced when biomass is used. Third, it supports sustainable energy transition by converting waste materials into useful energy products and supporting renewable energy system. Lastly, synthetic fuel contribute to economic benefits through industrial development, job creation, and better utilization of local natural resources. Synthetic fuel have many applications across different industries. In the transportation sector, synthetic diesel, and jet fuel can replace conventional fuel in car, truck, buses, ships, and aircraft. In power generation, synthetic fuel are used in gas turbine and industrial boiler for electricity production. In the chemical industry, methanol and syngas are used as raw material for manufacturing chemical and fertilizer. Synthetic fuel are also important in aviation and military application because they provide high-performance fuel and ensure fuel supply stability for strategic operation.
Hi, hello, my name is Ashraf Muhammad Yusuf with the matrix number 230699. So for part 2, I will be explaining upon the process flow diagram and also process description. So basically, in the synthetic fuel industry, the conversion of raw solids or gases into liquid fuels involves 5 critical stages. The first one, which is feedstock preparation, then we have gasification or reforming, then third we have less cleaning and conditioning, and then Fischer-Tropsch synthesis, and lastly upgrading and distillation. So for the first step, which is feedstock preparation, for pre-processing efficiency, before conversion, raw materials must undergo crushing and grinding to increase the surface area for the reaction. and then undergoes drying, which is removing moisture to prevent energy loss during gasification. And lastly, we purify the components, which is removing inorganic ash and bulk impurities. A little thermodynamics note: moisture removal is a high latent heat process requiring careful energy integration. For the second step, we have gasification slash reforming. So in the synthetic fuel industry, we produce syngas. Feedstock is converted into a mixture of carbon monoxide and hydrogen. So for the chemical reaction, it's carbon plus water that converts into carbon monoxide and also hydrogen. This is highly endothermic process requiring temperatures above 800 degrees Celsius. Thermodynamics dictates that high temperature favor the equilibrium towards the gaseous syngas products. Okay, for the next step, we have gas cleaning and also Fischer-Tropsch synthesis. So for the cleaning part, we have to do a sulfur removal. Sulfur compounds are catalyst poisons and must be removed to ppb levels. We also remove by using the water gas shift method, which is adjusting the H2 over CO ratio to optimize for the downstream Fischer-Tropsch catalyst. And lastly, we have a particulate removal, which is removing fly ash and tars to ensure system longevity and product purity. So for the Fischer-Tropsch synthesis, we know that it is an exothermic chemical reaction which gives a negative 165 kilojoule per mole. The heart of the process, which is 2n plus 1 hydrogen plus n carbon monoxide, becomes CnH2n plus 2 plus NH2O. This is a reaction kinetics and thermodynamics are balanced to maximize chain growth. Last but not least, we have the product upgrading and also storage of the synthetic fuel. So refining and fractionation. Crude synthetic liquid is separated into marketable fuels using fractional distillation. Firstly, we have hydrocracking, which is breaking down heavy waxes into diesel-rich molecules. And then fractional distillation, which is separation based on boiling points in vapor-liquid equilibrium, which is VLE. Isomerization, which is rearranging molecules to improve octane ratings.
Now I will explain the role of thermodynamics in this process. Thermodynamics is important because it helps us understand how energy and heat move throughout the system. In chemical engineering, every reaction either absorbs or releases energy. First, thermodynamics determines whether a reaction can happen naturally by evaluating reaction feasibility. Second, it helps optimize operating conditions such as temperature and pressure to achieve higher conversion and better product quality. Lastly, understanding thermodynamics improves overall process efficiency by reducing energy consumption and maximizing output. Without thermodynamic analysis, industrial processes would become inefficient and difficult to control. Gasification is strongly influenced by thermodynamics because it is an endothermic process. The overall reaction can be represented as biomass plus heat plus limited oxygen produces syngas consisting mainly of carbon monoxide and hydrogen, together with smaller amounts of carbon dioxide and methane. Because it is endothermic, heat must be supplied continuously for gasification to occur. When temperature increases, equilibrium shifts and promotes greater syngas production. Important thermodynamic concepts include enthalpy change, heat transfer, and chemical equilibrium. By controlling temperature properly, syngas production can be maximized and process performance can be improved. After gasification produces syngas, the next stage is Fischer-Tropsch process. This reaction can be represented as carbon monoxide reacting with hydrogen to produce hydrocarbons and water. Unlike gasification, this process is exothermic, meaning it releases a large amount of heat. The purpose of this stage is to convert syngas into liquid fuels. Because heat is continuously released, temperature control becomes very important. Excessive temperature can reduce catalyst performance and affect product selectivity. Thermodynamic concepts applied here include Gibbs free energy, which determines reaction feasibility, and equilibrium conversion, which predicts achievable conversion. Proper thermal management ensures efficient fuel production. The final stage involves distillation. Distillation uses thermodynamic principles to separate components according to differences in boiling points. The process operates based on vapor-liquid equilibrium, where vapor and liquid phases exist together under equilibrium conditions. Heat supplied through the reboiler vaporizes components, while condensation occurs at the top of the column. Important thermodynamic concepts include latent heat and energy efficiency. Thermodynamic analysis helps reduce energy use while maintaining effective separation performance.
So, what have we learned from this thermodynamic analysis? First, we gain a solid understanding of energy conversion principles, how the chemical energy locked inside coal or biomass is transformed first into thermal energy during gasification, and finally into the chemical energy of liquid fuels. Second, we learn about critical importance of heat management. We have to carefully balance the endothermic heat requirement of the gasifier with the massive exothermic heat released from the Fischer-Tropsch reactor. If you don't manage this heat properly, this process becomes inefficient or even unsafe. Third, we explore chemical equilibrium behavior. We saw how manipulating temperature and pressure can shift equilibrium to favor syngas production or maximize our desired hydrocarbon fuel. And finally, we learn how all these principles come together to optimize process efficiency and support the production of sustainable fuels. It is this deep to understanding that allows us to design better, more efficient plants. Despite its potential, the synthetic fuel industry faces several significant challenges. The most obvious is the high production costs. These plants are incredibly capital intensive, and the fuels they produce are currently much more expensive than the conventional crude oil derived gasoline or diesel. Secondly, there's the issue of high energy consumption. The entire process from feedstock preparation to gasification to product upgrading requires a substantial amount of external energy, which reduces the overall well-to-wheel efficiency and increase operating costs. Third, we must address carbon dioxide emissions. Where we use fossil feedstocks like coal or natural gas, the process generates a significant amount of greenhouse gases, which directly conflicts with sustainability goals. Finally, we rely on expensive catalysts and specialized equipment. The Fischer-Tropsch catalysts, often made of cobalt or iron, are costly and can be easily poisoned by impurities. Combined with the needs of high-pressure, high-temperature reactors, this makes the technology economically risky. Looking ahead, the future of synthetic fuels is actually very promising. Thanks to several emerging innovations, the most exciting development is green hydrogen integration. Instead of using fossil fuels to produce syngas, we can use renewable electricity to split water into hydrogen and then react with hydrogen that captures carbon dioxide to create synthetic fuels. This is the power to liquid concept. We are also seeing a major push towards biomass-based synthetic fuels. By using agricultural waste and sustainable biomass, we create a fuel cycle that is close to carbon nature. To tackle the emissions problem, carbon capture technology will be essential. We can capture the carbon dioxide produced during gasification and either store it underground or even better, recycle it back into the reactor to produce more fuel. Finally, the expansion of sustainable aviation fuel or SAF is a huge driver. Aviation is a hard to electrified sector, and synthetic jet fuel is currently our best bet for decarbonizing long-haul flights. In conclusion, we have established that synthetic fuel is an important alternative energy source, particularly for sectors like heavy transport and aviation that are difficult to electrify. It offers a viable path to reduce our dependence on crude oil and improve energy security. However, we have almost demonstrated that thermodynamics is absolute essential to this industry. The principles of enthalpy, equilibrium, and heat transfer govern even major steps, from the gasification of the feedstock to the Fischer-Tropsch synthesis and even the final distillation and separation of products. Ultimately, a thorough thermodynamic analysis is the key to improving efficiency and sustainability. By understanding the energy flows and losses, we can optimize operating conditions, reduce waste, and make the process more economically viable. While challenges remain, the integration of thermodynamics with new technologies like carbon captures and green hydrogen give us a roadmap for the future. That's all from us. We are from Future Billionaires. Thank you and have a nice day.